So let's begin. Two-dimensional graphs. So when people talk about graph visualizations, they almost always mean two-dimensional graphs. There are many really good packages for doing this, so I'll just name a couple of them, Gephi and Cityscape. Both are open source, both run inside, both are written in Java, so they run inside a Java runtime environment. So that means they're kind of slow, but they're really good. So because they run inside Java, they are multi-platform. You can run them on pretty much any machine. And they're really, really impressive. 2 months ago, I gave a webinar on Gephi. And you can go back and take a look at my notes. So I have the full presentation online at this address. By the way, inside the slides, when you download the slides, these slides, and open the PDF, all web links, all URLs are clickable, so you can actually click on it, and it'll take you to the corresponding web page. So a visualization you see here in this slide is a visualization. Well, this is a geographical network of postal correspondence in Europe. Which I took from one of the online blogs. And this is typically what people see when they do a two-dimensional graph visualization with Gephi. Really, really powerful, really nice, has a lot of built-in statistics to calculate various measures. So if you want to extend this to 3D, you don't really have that many options. Well, the first thing you might want to ask yourself, do you really want to do these graph visualization in 3 dimensions? There are pluses and minuses to taking graphs to 3D. So in 3D, imagine this graph being in 3D and have various communities and links between them. So in 3D, you have an option to rotate this object around the vertical and horizontal axis, but almost always some of the structures will be obscured by other structures. Simply, that's the nature of three dimensions. So if you're fine with that, you can certainly rotate things. You can make them somewhat transparent and see through them. So I personally really like an option of looking at graphs in 3D because it gives you an ability to see everything you can see in 2 dimensions. Well, a 2-dimensional graph is simply a projection of whatever you have in 3 spatial dimensions. But you can also rotate the object and zoom in on various features and so on. And also adding a 3rd dimension lets you encode one additional attribute. So you can imagine, for example, a 3-dimensional graph being a 2-dimensional graph where the 3rd dimension encodes something else. And I'll show you some examples along these lines towards the end of this webinar. All right. So assuming that you really want to do 3-dimensional graphs, which I think is a nice thing to do, what are the packages that are available to do this kind of visualization? Well, if you search, for example, for Gephi and 3-dimensional visualization, you will find one of the first links will be a plugin called Force Atlas 3D, which claims that it can do 3-dimensional visualization in Gephi. Well, it's not entirely accurate. So what it does, it actually gives you a 3-dimensional look and feel. So your nodes will be spheres and you have proper lighting. You can adjust the direction of lighting and so on. And you can actually select a number of 3-dimensional layouts. But what you see is really a 2-dimensional. So it gives you the proper perspective. The nodes that are further away will be smaller. But in practice, you can't interact with a 3-dimensional scene inside Gephi with this plugin because Gephi has been originally written as a 2-dimensional package. So you can, for example, spin the network in 3D. So there are various tools for visualizing brain networks, functional brain networks. So for example, if you Google Connectome Viewer, you'll arrive at this web page. And these are really, really powerful tools, but they're somewhat domain specific. So they let you visualize regions of, inside brain, regions of similar electric activity and connections between them. Really, really interesting visualizations. And you can certainly adapt these tools to your workflow, but they're really specific to one single task. There is a package, so of all the tools that I found, so I did quite a bit of research preparing for this talk, and of all the tools that I found online, the one which stood out was Graph Insight, really impressive. So it was a fantastic tool. It had a free academic license, embedded Python shell, so it could actually do things interactively or script everything. But unfortunately, it no longer exists. So it looks like it was developed by a startup a few years ago, and then the startup got purchased by a bank 3 years ago. And although the tool, you can still go to YouTube, for example, and Google Graph Insight, and you will find a lot of demo videos, but the tool is no longer available, unfortunately. You can download still a demo version, but it's somewhat it's very limited. So another tool which is quite impressive. It's called Walrus, and it was a research project to do exactly what we're trying to do here: visualize graphs in 3D, so collection of nodes and links or connections between them. Unfortunately, this tool was written about 15 years ago, and the last update was done in 2005. So people report problems trying to compile it on modern operating systems with modern libraries. So unfortunately, this tool is it was a research project, was pretty impressive, but it's not well, essentially no longer available. And then there are a number of other tools. So BioLayout Express 3D is kind of interesting. It was written in Java, but similarly, development on so it was completely open source, but development stopped on the open source version stopped in 2014, and now they only maintain the commercial version. You can purchase it. It's pretty good, but it's $500 for desktop license, which can be prohibitively expensive to many people. And then there are a number of research projects. So if you Google, for example, 3D graphs or WebGL or 3D graphs JavaScript, a lot of people have various things online. Kind of impressive. The problem with these is that it's kind of difficult to code in JavaScript and WebGL if all you want to do is just visualize a simple graph. And this is probably not the way you want to go, simply because it's not really ready to end users. So if you pose a question, is there any good open source cross-platform currently maintained, user-friendly, and dedicated three-dimensional graph visualization tool? The answer appears to be no, unfortunately. And the reason for this is that the vast majority of people, when they want to visualize graphs, they are perfectly happy with 2 dimensions. They don't know what they're missing, of course, if they can take these graphs to 3 spatial dimensions. But the topic of this webinar is 3-dimensional graphs. So what can we do to visualize these structures in 3D? So as I mentioned, you can certainly code everything from scratch using JavaScript and WebGL. And maybe there are some tools for some libraries for simplifying this task. I haven't really seen anything that is user-friendly. There's a tool that we're going to use today, which is called NetworkX. It's a Python package for building graphs, doing graph statistics, and doing a little bit of visualization. You can combine NetworkX with a 3-dimensional package called MyVI. And for example, there's a web page. Again, if you click on anything inside the PDF, it will open the web browser. So let me just take you to that web page. Here's a web page, and there are YouTube videos. And this is exactly what we want to do, so visualize 3-dimensional graphs. I tried to play with 3-dimensional graphs in MyVI, and I found there are bugs in MyVI implementations, which if you do any complex visualizations, they slow down the MyVI shell. So the terminal where you have Python open and typing MyVI commands, it becomes kind of slow, and it becomes painfully slow. So unfortunately, there's a bug which seems to be present both in Mac and Windows implementations, and I haven't seen it corrected yet. A colleague of mine suggested using a tool from chemistry called JMOL to visualize 3-dimensional graphs. So if you think about it, in chemistry, what you're really visualizing, you have a collection of atoms and then molecular bonds between them. So you have a collection of nodes and edges or links between them. And this is very similar to graph visualization. So you can certainly use JMOL for this task. The only downside is that JMOL was written with chemistry in mind, so if you're working with this interface, you will be running against a lot of chemistry annotation, which is might not be exactly what you want. But this is certainly one option. What we're going to do today, we're going to use NetworkX package, a Python package that I mentioned before, VTK, a 3-dimensional graphics library for Python, Java, C++, and ParaView, which is a general purpose visualization tool. So basically, we'll build up a workflow which uses, except for NetworkX, a workflow that uses general purpose 3-dimensional, really powerful 3-dimensional visualization tools. And of course, you can use these tools. They were not developed specifically for graph visualization, but as it turns out, you can actually do quite a lot to visualize graphs using this pipeline. So the nice thing about NetworkX, VTK, and ParaView is that everything is scriptable. So I'll show you a lot of examples of scripts, or you can automate things and just put everything into state files and load a state file, and here comes your visualization, and so on. They are really scalable. Everything I show you today will scale beautifully to hundreds of thousands of nodes without any problem. And you can certainly, with a little bit of care, you can certainly extend that into tens of millions of nodes. And if you want to visualize billions of nodes, you can certainly do that as well. So talk to me if you have that problem, and I can help you. The main disadvantage of this approach is that because ParaView and VTK were not designed from scratch to handle graphs, on networks. Your visualizations will be kind of static in 3D, so you can certainly zoom in and zoom. You can spin it around. You can color them in various, color them by various attributes. But you can, for example, click on a node and highlight its connections. So for that, you would need a dedicated graph visualization tool. And also one note, so everything I'll show you today, the edges, the links between nodes will be straight lines, but you can certainly encode arcs as well or other types of lines with a little bit of programming effort. So the workflow is the following. We're going to use Python and NetworkX to create a graph, position nodes, optionally compute some statistics using NetworkX functions. And then we're going to store that as a VTK file using a code that I'm sharing with you. I'll show you the code to you in a few slides. And we'll do that in Python 2. I'll actually use Python 2.7. And the reason for that, why I'm not using Python 3 in this presentation is, well, you actually can, but as it turns out, VTK for Python 3 is still in active development, so it hasn't been finalized. I'm using, when I do teaching, I use either Anaconda or Miniconda, which are very nice Python distributions. And unfortunately, they don't include VTK for Python 3, so that's the reason why I'm sticking to Python 2 in this presentation. But in principle, you can certainly download VTK for Python 3, the source code, and you compile it yourself and do everything, all these exercises in Python 3 as well. And then so we'll load, once the VTK file is written, we will load it into ParaView, and then we can do a lot of nice three-dimensional visualization. All right. So a few words about VTK. As I mentioned, VTK is a three-dimensional visualization library, stands for Visualization Toolkit, that is very, very popular. It's been in active development since '93, more than 20 years, and it's cross-platform. There are interfaces for working with it from C++, Python, Java, and Tcl to CLTK. It supports a huge number of various visualization techniques and processing algorithms, filters, for polygon rendering, ray tracing, and lots of other things. So really, really powerful. And so my day job is scientific visualization for Compute Canada, and we use VTK a lot. It supports many different data types. So it was originally developed for visualizing objects that have some spatial extent. So basically, you might have a scalar field or a vector field or a tensor field or, I don't know, tensors of tensors, so really complex. And these fields are defined on some type of mesh or discretization in 2D or 3D. Could be a collection of particles, structured or unstructured meshes. And then it supports parallel processing and parallel I/O. So originally, VTK and the tools that are built on top of VTK were developed for processing visualizing very large data sets. And so the tools that routinely use VTK are, well, I already mentioned MyVI. MyVI is a really nice package for desktop three-dimensional visualization. As I mentioned before, it has some bugs, so that's why I don't use it routinely. And also a couple of really nice general purpose tools. So I already mentioned ParaView. Is it very similar to ParaView? Everything, so we'll use ParaView today, but you can certainly use Visit to visualize everything we do today as well. So in VTK, you can store a large number of different data types. So you can store data on a Cartesian mesh, on a rectilinear mesh, or on a structured curvilinear mesh, on particles, on polygonal data, on unstructured meshes. The two data formats that are important, that are interesting to us today are the two last ones, polygonal mesh. So in polygonal meshes, basically you have a collection of two-dimensional cells that are defined either in 2D or 3D. So you define a collection of points and then some type of links between these points. And unstructured grid unstructured mesh is exactly the same, except in 3D. So in 3D, basically you have a collection of three-dimensional cells, could be cubes, could be tetrahedra or something else. So again, a collection of points in 3D that you connect in some way to define cells. So both polygonal data and unstructured meshes can be used for defining graphs, because a graph is basically at the core a collection of points, and then you have some links between these points. And then we're going to use ParaView as a front end to VTK classes, to VTK data structures, and ParaView has a very nice interface. So it has somewhat of a steep learning curve. That's why we actually teach ParaView in series of traveling workshops. So I usually go several times a year to different universities and give full day ParaView workshops, but you can certainly find a lot of documentation online as well. It's an open source package. That means there are online forums, and you can certainly download the source and compile it, and really, really good online documentation as well. To repeat the slides in these, to repeat the exercises in this presentation, you will need to have ParaView installed. So I'm not asking you to install ParaView right now because it's going to take some time. So I suggest that you just relax, kick back, and watch this presentation. But you can certainly, so in the zip file that of this presentation that you downloaded, there are 15 files. There are lots of, there are many different scripts, and you certainly in your spare time after this presentation, you can try to install ParaView. You also need to install Python and a couple of Python libraries, so VTK and NetworkX, and then you can repeat all the exercises that I mentioned that will show in this presentation. I suggest when you install, if you've never used Python, if you've never used any of the Python libraries, you're still good to go. You can still just run the scripts that are supplied in the zip file. You need to, so as I mentioned, you need to install 2 libraries, and the way I suggest, if you've never used Python before, the way I suggest to install things is I suggest to download a mini conda Python distribution, which is fairly lightweight. It's only 100-something megabytes, and it doesn't include any packages. Once you install it, you can install it on Windows, on Linux, on Mac. You will open a shell, so in Windows it'll be just the DOS prompt. In the Unix operating system, it's going to be a Unix shell, a Unix terminal, and then you will type something like this: conda install VTK, conda install NetworkX, and this will work on all platforms, including Windows. That will install the packages that you will need, and then if you want to check your installation, just start Python from the same command line, and type commands import VTK, import NetworkX as NX, and that will let you test whether the installation went correctly. So here I'm starting Python inside the Mac OS terminal. And this is Python 2.7, as you can see. So I'll just type import VTK, and that should not complain. That should import the library. Yep. And then import NetworkX as NX, and that worked as well. Yeah, wonderful. So everything is installed and will work properly. All right. So NetworkX, as I mentioned, it's a really, really good Python package for creation, manipulation, and analysis of complex networks. It's open source. It has really nice documentation at the following address. So we've already loaded into our Python shell. If you want to check all the methods, so basically all the attributes and all the functions that come with this package, you can simply type the following Python command: dir nx, and it will open hundreds of names. So these are names of various attributes and functions that come standard with this package. What I'm going to do now, I'm going to use what is called Python's list comprehension to create a smaller subset of this list. So I will only list the types of graphs that are built into NetworkX package. And to do this, I will type the following command. So I will create a list, and let me just move it a little bit up so you can see the bottom of the screen. So I'm listing everything, all elements, inside the output of the previous command. If those elements have underscore graph inside them, so if underscore graph in X, then close the list. So basically, this command will create a smaller subset of all functions that have underscore graph in them. And as you see, there's quite a lot of output, so we can actually count these, just do length of on the output. There are 105 built-in graph types, so really nice to have all this functionality. If you're just curious, if you want to play with the different types of graphs, and we're going to do that in the next few slides, you can certainly try to invoke these graphs and then try to visualize them. So a lot of functionality comes standard with in NetworkX. And next, I also want to show you the types of layouts that are standard in NetworkX. So I'm going to run the previous command. I'm just going to replace underscore graph with underscore layout, and that will return 6 functions. So I'm actually counting here. Let's return the functions themselves. So here's a subset of the longer list showing the layouts available in graph layouts available in NetworkX. So layout, if you've never done any graph visualization, layout is simply an algorithm for positioning nodes. So basically, it's an algorithm to calculate X, Y, or X, Y, and Z in 3D coordinates of nodes, and you can do nice things and nice things to your graph, so that it's displayed beautifully in 3D. So one note here is that the layout, which is called Spring layout, and the Fruntemann Ringgold layout, they're actually the same layout. For some reason, they have a separate name for it. So this layout has been designed to, I'll give you several examples. This layout has been designed to maximize the amount of space that your graph covers in 2D and 3D. So you can also use, I'll show you several examples. You can use third-party layouts as well, and there is a very easy way to incorporate this into your Python code. So circular layout, random layout, and shell layout are fixed static layouts. Basically, they produce a set of X, Y, and Z coordinates. Well, X, Y, and optionally Z coordinates. And you can't really introduce any forces in these layouts. On the other hand, Spring layout and Spectral layout are force-directed layouts. So basically, here you treat the graph as a collection of n-body points that can move around, and then link nodes attract each other, and non-linked nodes are pushed apart. So you have attractive forces and repulsive forces acting on nodes, and that will produce a given, well, a specific layout. So the coefficients and the types of forces that act on the nodes, they depend on the layout. Today we're going to look only at two force-directed layouts: the Spring layout and another one, a third-party layout called Force Atlas, that will produce nice effects. So let's generate a simple graph and see how these layouts work. I will I'll just retype this command. So I'll say graph, let's call it H, is equal to, let's call a function built-in graph for a random graph. So GNM underscore random graph. And so we're building a random graph with 10 nodes and 50 connections, 50 edges that build a graph. And now we can apply a layout. So a layout, basically an algorithm for positioning nodes. So let's apply a shell layout first to it. I'll say NX shell layout. And then I can supply, so I need to supply the name of the network. It's capital H. And then I need to tell it that we're working in 3 special dimensions. And then I hit enter. And what it returns is a collection. It's actually a Python, what is called a Python dictionary. So this is a collection of items, and each item is indexed by, in this case, by the nodes index. So there are 10 nodes, right? Because we asked for 10 nodes and 50 connections. So there are 10 nodes indexed from 0 to 9. And for each node, we have a collection of an array of 2 elements. And these actually X and Y positions of the nodes that are being computed by this layout. So notice that we asked for 3-dimensional layout. So we passed dimension is equal to 3. But as it turns out, this layout was only implemented in 2D. So for example, if we say, what are the X and Y, what are the coordinates of the very first node, they are going to be 1 and 0. So the first node will be positioned at this specific location. So unfortunately, the shell layout and the next layout, circle layout, were only implemented in 2D, even though you can pass dimensions equal to 3 to them. So on the other hand, the Spring layouts, random layout, and Spectral layout were originally devised for both 2D and 3D. So for example, if you call the previous command, and let's change shell layout to Spring layout. So I'll take Spring layout here. It returns 3 numbers, 3 coordinates, X, Y, and Z for each position. So you can actually readily use these for visualizing graphs in 3D. All right. So as I mentioned, so we'll store data as VTK file, but to actually to write data to VTK, you need to have a proper Python code. And I wrote a code. It's a function called writeObjects. It's stored inside the file write-node-edges.py, which is part of the zip archive that you downloaded. And the way it works, so there is one argument that you need to pass to it. It will be a collection of points. So the first argument, node coordinates, is a list of lists. So basically, it's a list of points, and then each point will have a list of X, Y, and Z coordinates. and this will define the position of the nodes. Then optionally, you can pass a list of edges as well. And the list of edges, so a list will contain a number of items, and each item will contain two indices of the starting and the ending point of the corresponding connection. And then optionally, we can pass two attributes to associate two attributes to the nodes. So for example, each node can have a, I don't know, eigenvalue degree or regular closeness or closeness degree, number of connections, and so on. So various attributes you can assign to nodes. I implemented only two attributes, but in principle, it's very easy to modify these to have as many attributes as you want. So each attribute is basically a list of items, list of numbers that you associate with nodes. Then optionally you can pass the name of the corresponding attributes. So that name is actually visualized, well, that name is available as a function, as a variable name inside ParaView. And then power is in power index. So the idea of a power index is if you want the radius of the node to be proportional to whatever attribute value you're passing, you use power 1. If you want the volume of the node to be proportional to the attribute, you use power equal to 1/3 and so on. So basically it's a power to modify the scaling of the radii of individual nodes. The same for the second attribute, so scalar 2, name 2, power 2. Then optionally you can pass node labels to pass names to individual nodes. And then you need to select which method we're going to store the data in. So I mentioned before that you can either store graphs as polygonal data, two-dimensional polygonal data, or as three-dimensional unstructured mesh. Both types of data formats are implemented in this function. So which one you choose is completely up to you. There are certain limitations that come with each format. So for example, you cannot apply a tube filter to an unstructured mesh. You can only apply it to VTK polygonal data, as I'll show you very soon. And then finally, the last argument is the name of the file that you're writing to, and then it will automatically be given an extension, either VTP.vtp or the VTU, depending on whether you're writing polygonal data, two-dimensional polygonal data, or three-dimensional unstructured mesh. All right. So here is our very first example of a graph. So it's a random graph. Excuse me. We're asking Python to build a graph, NetworkX to build a graph with 100 nodes and 500 edges, 500 connections. And then, so we use the GNM, same routine we used before, random graph to generate the graph. Then we're printing the number of nodes. Well, actually, sorry, we're listing all nodes, so the full list of nodes. Then 100 nodes. We're listing all 500 edges. So there will be quite a lot of output when we run this code. And then we call a random layout in 3 spatial dimensions. So we pass the graph, pass for 3 spatial dimensions. The layout returns a dictionary of positions keyed by the node, as I mentioned to you before. And we actually, to write that to VTK file, you want to convert it to a list of positions. So we use another Python list comprehension to convert that into a list of positions. And then we optionally call a function degree values to calculate the degree of each node. So degree is basically a number of connections that node has, inbound or outbound connections, total number of connections. And then finally, we write that object. So we write the positions of the nodes, X, Y, Z, the list of edges, the attribute, which is going to be the degree, and then we'll call it degree. So the name, the variable name degree appears inside ParaView. And then we're writing into a file called network, which will be given the proper extension. All right, and then when you import that into ParaView, you will have a picture similar to this one. So a 3-dimensional graph that you can spin around. And let me do that. So I'll switch to to my terminal. I will exit Python shell because I just want to run this script. So I'll call this script, and the script is called randomgraph.py. So I'll just say Python randomgraph.py. Remember that it will output the full list of nodes and full list of edges. So there will be quite a lot of output. There are 100 nodes, a lot of output, and 500 edges. So I won't scroll through the whole thing. So the bottom line here is that it produced a file called network.vtp, which, as you can see, has the proper timestamp. It was produced just now, and it stores the 3-dimensional graph inside a VTK file. So now we want to import that file into ParaView, and here you have several options. So you can either import it by hand, then you will apply a glyph filter to put a sphere on top of each node. Then optionally you can apply a tube filter to make the nodes, the lines, the connections thicker. And then optionally you can adjust the glyph properties and the tube properties. Or already prepared a ParaView state file, which is called drawgraph.pvsm, that you can simply say, open ParaView, then go to File, Load File, load that state file, and it will have the visualization. Or if you're working on a Unix-based system, Mac or Linux, you can simply do everything in a single command. Just type in the command to call ParaView, and then say --2 state is equal to, and the name of the state file that you're loading. So I'll go through all these options. I'll show you how this works. So that you can actually, starting from the simplest option, so that you can actually see for yourself how it works. So I'll run this command before. Let's see, here it is. So I call a command to start ParaView, and then I'm passing the name of the ParaView state file, drawgraph to it, and then everything should work automatically. I'm working with two screens, so I need to drag my ParaView screen to the shared display. So here we go. Here we have three-dimensional objects. The nodes are displayed as spheres because we placed a glyph object on top of each sphere. And then the connections are displayed, the connection between spheres are displayed as thick lines. The spheres are sized by the degree. Remember, we calculate the degree, the number of connections each node has. So basically, the more connected a node is, the bigger it will be. And radius is proportional to the degree. And we'll also color them by a degree. So I'll bring up the color legend. Let's see where it is. I need to click on glyph. Here's the color legend. So basically, the higher the degree is, and degree goes from 3 to 17, the redder the node will be. So nodes that are not very well connected are small and blue. The nodes that are well connected are red and large. And again, everything is modifiable, so you can certainly adjust the colors. You can adjust the line thickness. So, for example, I click on glyph, and let's say I want to make the node smaller. I just hit on apply, change the size here in the properties of the glyph filter. If I want to make it back a little bit larger, then here we go. And then if I want to click on the tube filter, I can make the tubes thicker. Let's make them slightly thicker. So adjust the thickness, hit on apply, and here we go. And as you can see, the whole thing is three-dimensional. You can actually interact with it in 3D, and everything looks beautifully. Optionally, you can change the transparency of everything, and do anything you normally do in ParaView. So let's adjust transparency of the tubes, which should be right here. So right now it's set to 0.47, so 1 being non-transparent, 0 being completely transparent. So let's make it less transparent, for example. So here we go. And of course, you can adjust the colors of everything. So we can make the edges yellow or anything you want. So one thing I want to, let's make them white. I prefer white again. And now what I want to mention next is you can actually display the labels of individual nodes. So in ParaView, unfortunately, it's not a single button operation. You have to follow a certain procedure. But once you get used to it, it's fairly easy, and it makes sense. So to label a node, what you have to do is you need to press back in the visualization window. You need to press V to start the Find Data dialog. And you want to select the nodes that you want to label. First, so we have cells in ParaView and points, so we're working with points right now, nodes. And we want to select those nodes which have certain characteristics. So for example, let's just select all of them. So ID is greater than or equal to 0. And we'll click on Run Query. So that returns a list of nodes, takes a couple of seconds. And then what we want to do, we want to make the original data set visible. Right here, I click on the eye icon next to the original data set. Let's go back to the previous dialog. And then here, I want to say point labels by their ID. And here we go. So now the labels actually, so each node has a label, and the labels are simply numbers going from 0 to 99. So let's click on the tube filter, and let's reduce transparency of the connections, so that actually I want to also set the opacity of the regional data to a low value, so that we don't have everything displayed at the same time. Okay, here we go. So that's what I wanted to show. Okay, so here we have connections, three-dimensional connections. We can interact with it with this graph in 3D, and then we have everything labeled properly. Let's say if we want to label only nodes that have degree higher than 10, nodes that have 10 or at least 10 lines, well, 10 connections. We can certainly do that as well. So bring up the previous dialog, and we're only highlighting nodes, labeling nodes that have the degree that is greater than or equal to, let's say, 10. So that will only label the, so run selection query, and that will only label the biggest nodes, as you can see. So the biggest nodes have labels. The smallest nodes, that have 9 or fewer connections, don't have any labels at all. All right. So let's continue. Let's switch to Spring Layout. So in this presentation, I don't really want to show you the full source code of each Python script from scratch again and again, simply because this will be a lot of code. I will simply show you the differences. So I'm running here the standard Unix div command applying 2 file names to it. So it says that show the differences in the second file. Now it's called randomgraph2.py. So show the differences between the first file, randomgraph.py, and randomgraph2.py. So everything we do, so now we have a new file called new script called randomgraph2.py, and everything we do, we simply copied the first script, and then we changed the first a single line. So we had a line calling random layout function, and we simply switched to a Spring Layout, and we also supplied the following parameter k, which is what it is. Well, you can simply bring up a help. Let's go back to, I will kill ParaView here, and let's start Python and say import NetworkX as NX, and then bring help on NX. So we're now switching to Spring Layout, post-directed layout. So bring help on NX, oops, not sprint, but Spring Layout. And here it says, so k is one of the, there are lots and lots of arguments that you can supply to Spring Layout. And one of the arguments is k, so basically it's the optimal distance between nodes. So the higher the value is, the more pushed apart the nodes will be, and the opposite is true. So if for very small values of k, the nodes will cover a very small part of the, only a very small volume in 3D. So I'm going to run this. I'm going to switch back to the Unix shell, back from Python, and I will run a Spring Layout. So a force-directed layout where the nodes will be positioned according to some rule, according to some forces. So Python randomgraph2.py, and it will give me similar output. And then I promise to show you how to load everything from scratch. Let's do that. So let's open ParaView. And so next I will, again, it opens in a different window. So next I will load the state file by hand. So I'll say a file load state, and then it's sitting somewhere here. So draw graph. I confirm the location of the data file, and here we go. So here's the output of a force-directed layout where the value of k was sufficiently large, so the nodes actually pushed apart. And the visualization type is exactly the same. So the nodes are sized and colored by the amount of degree, by the number of connections they have. And as you can see, it turns out that the value of k is sufficiently large. We picked up number 1. And so that the nodes are actually sitting on top of a sphere in 3D. So for example, if we were to pick up, I don't know, 0.1 or 0.01 or something like that, the nodes will occupy a smaller volume in 3D. All right. So let's go to another example, Möbius counter graph. Here we have, we're calling a function, so predefined graph in NetworkX, and so the function is nx Möbius underscore counter underscore graph. We're not supplying any arguments to it. And then we are calculating, so everything, so we're copying the previous script. Actually, I have a typo here. It's just supposed to be random graph 2. And we're copying into a script Möbius graph. So we're changing the function that we're calling. So switching from a random graph to a Möbius counter graph. And then instead of printing all nodes and all edges, we're printing the total number of nodes and the total number of edges. And then we also print the degree for each node. So to run the script, I simply say Python Möbius counter.py. and it runs, it will output. So now it doesn't print the full list of nodes and full list of edges, only prints total numbers, so 16 nodes and 24 edges. And then the list of degrees of each node. So there are 16 nodes, 16 numbers here. All degrees are exactly the same. That's just the nature of this predefined graph. And now I will go to ParaView. And so let me start now load everything by hand so you can actually see how it's done. So I'll start ParaView. Again, need to drag it to the shared window, shared screen. Here we go. Oops. Yeah, here we go. So I will navigate to the data file. It's called network.vtp right here. Open the file. So hit apply. Nothing is visible, and the reason for this is that we need to actually, because I didn't hit apply. So this is not a very nice visualization because the points are not displayed. So the points are infinitely small. That's the nature of mathematical point. What we really want to do, we want to place a three-dimensional object on top of a point. So we'll call an object called a glyph filter, and we're placing a sphere on top of each object. So hit apply. Here we have spheres. Then let's color spheres by the degree. So notice the degree was passed to the VTK object, and now it appears as one of the variables inside your data file. So now we're coloring nodes by degree, and remember that all degrees were equal to 3, right? That's why, so all of them are equal to 3. That's why we have a single color. And also we can size them. So to size the spheres by a variable, you need to modify the properties of the glyph filter. So here what we do, I scroll a little bit down, and I see that the scalar that we're going to use is called degree. And then we're going to turn on the scale mode. So it's actually scaled by the amount of, that variable. And again, everything is the same simply because we have all degrees are equal to 3. Otherwise, if they would be different in this visualization. And then, so let's make everything a little bit smaller, all nodes a little bit smaller. So the scale factor, not the radius, but the scale factor right here. Let's just make it 3 times smaller, for example. All right, here we go. And then to make the line thicker, I apply the tube filters. So for example, I can go to alphabetical or to recent. It appears in the list of recent filters I worked with, and then hit apply. Oops, and also need to make the spheres visible. Again, so here you have, notice that we have 3 objects now. The original data set, the glyph, so basically the spheres, and the tube. And these are 3 different objects in the pipeline, and you can make them visible or invisible, completely up to you. So the tube now, let's click on the tube itself, and let's make it thicker. So that is done. There is a parameter somewhere, which is called radius, right here. So let's just increase the radius of the tube to 0.1, for example. Let's see why I don't see it, not sure. Let me try to apply it again. Oh, I know why, because I apply the tube filter not to the original data, but to glyph. I need to make sure to apply it to the original data because we want to convert the connections into tubes, not the spheres into tubes. All right, so I apply the tube filter to the original data, hit apply, and here we go. So now we have nice tubes and nice visualization of the graph, right? That you can view from different sides. Of course, you can zoom and unzoom, and you can do various other things as well. So for example, to zoom, if you have a mouse, you will have a scroll wheel on a mouse. You will use that to zoom and unzoom. I'm using a trackpad here, so I just press Control, and then I can drag, and now instead of rotation, it gives me zooming in and out. All right. So let's go to the next slide. I will skip. So the next slide is a complete bipartite graph. I will skip that because we have only 10 or so minutes left. So your own graphs, it's very easy to create your own graphs from scratch. So far, we've been using only predefined graphs, but you can certainly just supply a list of nodes and a list of edges. There are standard commands in NetworkX for doing that. Let me now show you a fun example of a somewhat more complex graph. So this is a fractal graph that is basically a generation which is called Drogovtsev-Goltsov-Mendes graph. And the simplest graph of this type will have only 2 nodes, 2 points, and a single line between them. So the next generation, second generation of this graph will have a triangle, will have 3 nodes and 3 vertices. And the way this works, so basically going from a previous generation to the next generation in each subsequent transition, each edge generates a new node. And then the new graph will be made by connecting together 3 previous generation graphs. So for example, the second generation graph consists of 3 third generation graph consists of 3 second generation graphs. The fourth generation graph consists of 3 third generation graphs, and so on. So this is a fractal graph where there's a well-defined mathematical algorithm for constructing the next generation based on the previous generation. To work with this graph, I wrote a Python code called dgm.py that builds that graph. So it uses, again, this graph is one of the predefined graphs in NetworkX, so we don't have to do anything to define it. We just use the corresponding NetworkX function. And then I'm applying another force-directed layout called Force Atlas 2 that is not part of NetworkX, but you can actually download it as a Python code, so it's available on GitHub at this address. And the idea of these Force Atlas 2, so again, so you have the network acts as a collection of n-body points where individual nodes can move based on the forces that are applied to these nodes. So the nodes that are linked attract each other, the nodes that are not linked push each other apart. But the forces are scaled in such a way that the resultant graph will consist of communities of linked nodes, and the nodes that are not linked very well will be far apart in 3D. And then, so we apply this Force Atlas 2 layout. It generates a Python dictionary that we convert to a list, and then we print out the total number of nodes and the total number of edges, and then we write that to a VTK file. All right, so let me run. Oh, so optionally, optionally. Let's see, optionally you have, actually, I'm sorry, not optionally. You need, when we run this from the command line, you pass a number to it, which asks to build a specific generation. So generation 1, 2, 3, and so on. And this is what visualization will look like. In this example, it's a 7th generation Duragovs of Adults of Mendes graph. So let's just do let's say a 5th generation, because it doesn't take as long to compute. And actually, most computing goes not into generating the graph, but into the layout. So I'm asking Force Atlas layout to calculate 100 iterations, and then the output, the positions, are actually the result of all 100 iterations. That's why it takes a little bit time to generate this. So on my laptop, generating the 7th generation graph takes about 15 seconds. 4th generation or 5th generation graph takes only around 2-3 seconds. So let's do the 5th generation graph, and then we'll load into ParaView. So I erase everything from ParaView, and then I'll go to the Unix shell, and I will say Python dgm.py. Let's generate the 5th generation Duragovs of Mendes graph. So it'll take a couple of seconds. All right, I generated the graph. It wrote it to VTK file. It says there are 123 nodes and 243 edges. So let's now load that into ParaView. For simplicity, I'll just load the state file, and then I will need to adjust the properties of the connections and the nodes. Okay, so click OK. Confirm the location of the file. And here we go. So here's the 5th generation graph. So we need to certainly adjust various things here. So let's make sure the glyphs, the spheres, appear larger. So I'll change the, let's see what I do. I will change the scale factor right here. Let's set it to 0.03. Hit apply. And then let's also make the nodes a little bit thicker. Sorry, not the nodes, the connections a little bit thicker. So I'll change the radius to, let's say, 3. Okay, here we go. So here's a nice visualization. And again, the node sizes are proportional to their degrees. So the degrees go from, just say, let's click on glyph and bring up the color bar. So the degrees go from, actually, sorry, let me go back to the slide and just double check. Yeah, it's not proportional, sorry. The volume, so we have power equal to 1/3. That means the volume is proportional to the degree of each node. So degree, just a reminder, is the number of connections each node has. So the well-connected nodes are colored in red, they are large. And then the less connected nodes will have the color towards the blue end of the spectrum. All right. So this is a three-dimensional graph, very easy to generate, very easy to view and interact with in ParaView. At the very beginning of this presentation, I made a point that you can actually use the third dimension to encode something else. And we'll try to do that next. So I will run another script that generates a flat graph instead of a three-dimensional graph. It generates a very similar graph, but only in 2D. So I'll apply a two-dimensional layout to it. It's going to be exactly the same Force Atlas 2 layout, but we're asking now it to do it not in 3D, but in 2D. So the third dimension is going to be 0. We're going to generate a flat graph. Let's just see how it works. Let's erase everything from ParaView. Let's go back to the shell. And I will call Python DGM flat script this time. And just to double check, do I need to? Yeah, I need to supply the number as well. So we'll generate the fifth generation graph. We'll take a few seconds. And here notice that we have X and Y, and then the third index is 0. So that means that the graph is going to be flat. I will load the state file again. Hit OK. And here we have the graph. I will recent it. Click on one of these predefined buttons. And you see the graph is actually indeed flat, right? So the third dimension is 0. It doesn't encode anything. Optionally, we can actually make it useful by encoding some information in it. So what we do next, we have a script called DGM offset.py, which encodes a function of a degree. So a function degree of a given node to the power, so square root of degree divided by 5.7. And you will see that I'll produce some interesting result. So let's just erase everything from ParaView again. Unfortunately, in ParaView, there's no reload button. So even though every time we're reading from the same file, we have to load the state file so that the original data file is reread from scratch. So I will run the DGM offset. And again, 5th generation DGM offset script. Will take a couple of seconds. Okay, so the same 123 nodes and 243 edges, because mathematically it's exactly the same graph, but we're just playing with its layout by hand. So I'm going to load the graph again into ParaView. Confirm the location of the data file. And now you see an interesting thing happened. Now instead of the flat graph, we get a graph where things are offset nicely in the third dimension, and the offset is the exact mathematical function that I mentioned. So the offset, the nodes that have, so let's just increase the size of the nodes. So there's a scale factor somewhere, right here. So the nodes that are well connected are bigger. They have red color, and they are at the bottom of this z-axis, and the nodes that are not as well connected are actually at the top. And again, which function you use to encode the z offset is completely up to you. The point here is that you have the degree of freedom, and you can go from a two-dimensional graph, which is I guess one of these predefined orientations. So this is a two-dimensional graph that you would normally get in Gephi or Cityscape, and then you can actually use the third dimension to encode something useful, right? Here we go. All right, so we are running out of time. I will not be going through everything I have in the slides, but you can certainly look at the few remaining slides. I just want to briefly mention things that I don't have time to cover, and then we'll have time open for questions. So the next network that I was supposed to show is the social graph, which is also one of the standard predefined functions inside NetworkX, which displays the connections between different families in Florence. So the script is Florentine families.py. And here each node is indexed not by its number, but by the name of the family. So families like Medici and something else. And you can actually display these names inside ParaView as labels, using exactly the same mechanism I showed you before for labeling nodes. All right, and then how you can highlight individual nodes. So I mentioned at the very beginning that because ParaView and VTK are not dedicated tools for graph visualization, unfortunately, inside them, you can't really click on a node and then it will show its connections, something similar you have, but you can still do that by hand. So you can run a script that will show you that will highlight the nodes, will highlight the connections, the script, which is called Florentine families 2.py, and Florentine families 3.py will highlight individual nodes and also will highlight it its neighbors. And to do that, we're actually encoding information about the things we want to highlight inside the same degree list. So the nodes that are not highlighted have degree of 1, they will appear small. And then nodes that are highlighted have degree 3, and the neighbors have degree 2.5. And then what you do to that degree information is completely up to you. So you can either size the nodes, you can adjust transparency based on the degree, you can call them based by degree, and so on. So the point is you can actually highlight individual nodes and their connections and their neighbors, but that will be done, that has to be done programmatically inside the script as opposed to doing that interactively inside the GUI. All right, and then the final example, again, I don't have time to show it. It's an example of doing statistics inside NetworkX. So this is something that all of you, if you worked with Citoscape or Gaphy, you're familiar with. NetworkX similarly has a lot of built-in functions for calculating centrality. For example, in this script, I take the fifth generation Rogastov-Goltsov Mendes graph, and I calculate so I display its degree. For each node, I visualize the degrees, the number of connections, and also for each node, I calculate what is called the eigenvector centrality, which is a measure of how well connected a node is. So a node will have high eigenvector centrality if it's connected excuse me, to other nodes that have high eigenvector centrality. So that means that to actually calculate this measure for each node, you have to do it either iteratively by an iterative process until you converge to some static values, or you can do it by matrix operations. So that's what the function nx eigenvector underscore centrality does. And then when you run the script, you load the file into ParaView. You will see that now you have two variables. One is called degree, the other one is called eigenvector centrality. And you can actually do something, for example, size nodes or color nodes, or change opacity based on the information in these attributes. And there are lots of statistics. There are dozens, if not hundreds, of various functions for calculating degree, closeness, betweenness, current flow, closeness, and various other things inside NetworkX. And if you use it in tandem with VTK and ParaView, then you can actually visualize all these things as well. So that's it. That concludes the workshop. Sorry, I didn't have time to go through everything, but again, all source code, all scripts are available, so you can just follow all examples in your spare time after the workshop. No questions? Okay, well, thank you very much, everybody. So I'll stick around for a few minutes. You can certainly email me if you have any questions later on. If you have any trouble making any of these scripts work, feel free to email me at any time. Thank you.